Hello and welcome to my video on a proposed GEO belt optical space situational awareness CubeSat for the US Space Force. My name is Dylan Lurch. This is for a final project for Mechanical Engineering 597 at the University of New Mexico. Here's a brief overview of the mission objectives and requirements as outlined by the request for proposals. The satellite should be no more than 3,000 kilometers from objects in the GEO belt. The camera on the satellite shall have the ability to detect objects of the 13th magnitude or brighter. The camera should capture at least 20 stars per image when averaged across several images. The duty cycle of the camera will be 3 to 5 minutes per collect, with a goal of 3,000 images per 24 hours. The RFP specifies testing guidelines and requirements, and it also gives guidelines for the volume, mass, power, and cost requirements. This is the general work breakdown structure for the project. As you can see, we have a CubeSat GEO imaging mission. This mission is broken down into several parts. You have project management, which includes scheduling, managing, and budgeting the project. The space system, which includes the payload and the spacecraft bus. Ground system, which includes the ground station and all other communications from the ground. The verification and validation, which includes all of the testing for the CubeSat, and then mission operations, which are the pre-flight operations, flight operations, and post-flight operations. Next, we have the concept of operations, abbreviated as ConOps. This graphic shows the flight operations, so it begins with the launch, booster stage separation, the orbit circularization, final propulsion stage separation, and then you have the payload deployment and initializing all the systems. Next would be to orient the camera, so adjusting the attitude system so that it's aimed at the first target. Then we have the imaging of the GEO belt, so the full 2-year operation. At the end of the mission, we will begin the retirement process. To begin the retirement process, this design will use a single stage deorbiting solid rocket booster, and then after re-entry, the CubeSat will burn up in the atmosphere. So here we have a continuation of the ConOps overview. We have a little bit of a timeline here. So the project start would be January of 2024. And this goes all the way until March 2025 after launch. And then after the project operations, space operations, which you saw in the previous slide, this details the dates and the timelines for the retirement process. Continuing on in the ConOps, here we just have an overview of the task start and end dates. So as you can see, starting January, end of January of 2024, and then you see the re-entry burn-up ending sometime in January of 2027 after the retirement. Next, we're going to go into the orbital design. So here you can see the CubeSat orbital elements and the GEO belt orbital elements as assumed by the RFP. So you have the altitude, and then we're assuming that all of the craft or debris in the GEO belt are in a perfectly circular and equatorial orbit. And as you can see from the period and the velocity, there would also be geostationary. So for the CubeSat, you can see it's 3,000 kilometers shorter than the GEO belt orbit, and it's also perfectly circular and coplanar with that orbit. So to make the launch and maneuvering the minimum that it could be. And as you can see, the velocity is slightly faster than the GEO belt, so you would be able to image all of the objects after a 2-year mission. Here's just a graphical representation from this orbital mechanics software showing the GEO belt orbit, and then we have our CubeSat orbit. So it's right inside the ring there. So next we have the volume, mass, power, and cost budgets, abbreviated as VMPC. So just to reiterate the requirements from the RFP, it's a 3-unit CubeSat, so it would be 100 by 100 by 340.5 millimeters, and you have the volume here. The total cost needs to be less than 250,000 USD. The cost for the launch-ready spacecraft should be less than 150,000 USD, and the maximum cost for labor, testing, and facilities should be less than 100,000 USD. There aren't any specific power requirements, but it can be inferred that the power needs to be enough to run the satellite and the camera, and then the mass needs to be less than 4.8 kilograms. So here's a table showing both the overall requirements for volume, mass, power, and total cost, and then you have the utilized mass, power, and volume and total cost. Next, we have detailed descriptions of the components that will be factored into the budgeting. So I decided to use this Dragonfly Aerospace Gecko imager, a heater, which would need to be able to keep the satellite in operational temperature ranges because of it being near GEO orbit. It's a lot further than like a low Earth orbit satellite would be, and therefore would need a little bit more thermal capabilities. Then you have the deorbit module, like we talked about earlier. Then the bus mass would include the onboard computer, ADCS, commercial S-band antenna, S-band transmitter, and then solar panels. Diving a little bit deeper into the budgeting, we have the detailed mass budget. So here you can see the item, and we have each of the items listed, each of the items' mass listed, and then their percent of the total mass. And down here we just have the total and if the total mass meets the requirement, so less than 4.8 kilograms.